video, we're going to talk about half-life. The half-life of a reaction, or T1/2, is the time required for 1/2 of a given amount of reactant to be consumed. In each succeeding half-life, half the remaining concentration of the reactant is consumed. Here's an example: the decomposition of hydrogen peroxide. This is a first-order reaction, and this table shows decomposition over time. Our starting concentration at T = 0 is 1.000 molar. During the first half-life, which occurs from 0 hours to 6 hours, the concentration of hydrogen peroxide decreases from 1 molar to 0.5 molar. This means that half of our hydrogen peroxide is consumed. During the second half-life, from 6 hours to 12 hours, the concentration of hydrogen peroxide decreases from 0.500 molar to 0.250 molar. That means it decreases by half. During the third half-life, it decreases from 0.250 molar to 0.125 molar. The concentration of hydrogen peroxide decreases by half during each successive period of 6 hours. This simulation shows a visual representation. You see, we start with a bunch of coins, and one half-life later, we have 1/2 the amount of coins. Go for another half-life, we have 1/2 of that, and so forth. The AP Chemistry standards focus on the half-life of first-order reactions. And you will be given this formula on the AP exam. To find the half-life, you take 0.693 and you divide it by K. As you can see from the equation, the half-life of a first-order reaction is independent of the concentration of the reactant. However, half-lives of reactions with other orders depend on the concentration of the reactants, but these types of half-lives are beyond the scope of this course. Here's an example problem. Calculate the rate constant for the first-order decomposition of hydrogen peroxide in water at 40 degrees Celsius using the data given above. Looking at the image, we see that the concentration halves every 2.16 times 10 to the 4 seconds. And remember, sometimes half-life can be in seconds or hours or days, even years, depending on the substance we're talking about. We're asked to calculate the rate constant, so we'll take our half-life equation and rearrange it for K, like this. We're going to substitute in the half-life that we inferred from the image. That's the 2.16 times 10 to the 4th seconds. And then we're going to simplify. And our K is 3.21 times 10 to the -5 seconds to the -1. You're probably familiar with the term half-life being used to refer to radioactive decay. Well, the kind of half-life you see with radioactivity follows first-order kinetics. In summary, half-life is a critical parameter for first-order reactions because the half-life is constant and related to the rate constant for the reaction by this equation. Radioactive decay processes provide an important illustration of first-order kinetics.